Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. This is part 2 of the sequential circuits. We are going to learn latches much more in detail. In the previous session, we discussed sequential circuits which use memory elements. We saw that there are two types of sequential circuits, synchronous and asynchronous. Flip-flops and latches were used to build the synchronous and asynchronous circuits respectively. Later in the last session, we discussed the construction of SR latch using NAND. In this class, you are going to see how SR latch can be constructed using NOR gates. We will also share the working of another popular latch, D latch, towards the end of the video. Now, let us start with construction of SR latch using NOR gates. This construction is similar to the working of SR latch using NAND gates, but differ in certain perspectives. Let us note down the differences first. When we constructed the SR latch using NAND gate, the input S was connected to Q and R was connected to Q complement. But while using NOR gates, the input R is connected to Q and S is connected to Q complement. See the picture given. Here, I would like to add one thing to your notice. Different books and authors follow different ways of constructing latches using the NAND and NOR gates. So, this diversity is possible as long as the outputs of the SR latches does not violate the predefined conditions. So, please do not get confused if you see the construction of SR latches in other ways different from whatever is mentioned here. It is better to stick on to one method throughout your study. The next difference while using NOR gates is in the working of NOR gates itself. See the truth table of NOR gates. A NOR gate produces 1 only when both their inputs are 0 and in rest all the cases it produces 0. It is the opposite of the NAND gate. Now, let us see the construction using NOR gates. See the picture and the truth table before learning its working. Here is the truth table of SR latch using NOR gates. Here also there are 5 inputs in the truth table. One entry is getting repeated, which is that is when S is equal to 0 and R is equal to 0. In this case, you can have two different states depending on the previous state. When we discussed the construction using NAND gate, we encountered a similar situation, but that was when the inputs S and R was 1. As I told you, both the ways latches will work in similar manner, but the combinations of input values that will trigger the output will be different. This is because the gate which we are using is different in both cases. You can also notice that latch moves to an unfavorable state when the input of both the gates turns out to be 1. This is also a difference compared to the construction using the NAND gate. To understand the working of SR latch using NOR gates, take the gate whose input is having a 1 first. Because as per the property of NOR gate, if any of its input is 1, its output is definitely going to be 0 irrespective of the second input. To start with, let us assume that S equal to 1 and R equal to 0. If S equal to 1, then as per the truth table, the output of that NOR gate should be 0 and hence Q complement should be 0, and if Q complement is 0 and R, the external input is already 0, then Q should be 1. So, now we got the outputs, let us verify that. The condition of the latch is that its each output should be a complement of each other, and let us check whether it is valid in our case. Yes, it is, because Q and Q complement have values 1 and 0 respectively. This explains the first row of the truth table. When we used NAND gates, Q was 1 when the input S was 0. Here it is the opposite, the Q is 1 when the input S is 1. This difference is valid because we are using NOR, which is the dual of NAND gate. Dual of a Boolean is an expression that results when plus operation in Boolean changes to dot, and vice versa. And we will be seeing this change in the next combinations of inputs too. Let us check the next condition. What if S equal to 0 and R equal to 1? Here R equal to 1, then as per the property, the output of that NOR gate should be 0 and hence Q should be 0, and if Q is 0 and S, the external input is already 0, then Q complement should be 1. So, now the outputs are ready. Let us verify that. Here Q is 0 and Q complement is 1. So, this also satisfies the condition of complements. The third row of the truth table shows the same. Now, comparing it with NAND gated SR latch, there Q was 0 when R was 0, and in NOR gated SR latch it is the opposite. You know the reason why is it so? We had discussed it in the last case. What if both S and R are 0? In this case, we need to know the previous state of Q and Q complement to determine their present states. Recall the same situation that we encountered while using NAND gates. There the inputs were at a high state, here it is at low state or at 0. As done earlier, let us verify both situations. Suppose Q was 0 earlier, then Q complement must be 1. If Q complement is 1 and then the input gate R which is occupied with Q complement will produce 0 for Q. When Q becomes 0, the inputs of S gate are both zeros respectively. This in turn will produce a 1 at Q complement. So, the values of Q in this state is 0 and Q complement is 1, and that satisfies the condition of complements. And moreover, we learnt that the value of Q remains as 0 in the current state too. That is, previously S was 0 and R was 1, and when the inputs changed to 0, it did not affect the state and the latch continued to remain in the same state. Let us verify the next situation by setting the previous state of Q as 1, then Q complement will be 0. If Q complement is 1, then definitely the S gate which is coupled with Q will turn the Q complement to be 0. If Q complement is 0, then the output of R gate will be 1 because both the inputs to S are 0. So, we got the outputs as Q equal to 1 and Q complement equal to 0, which indicates that the Q and Q complement remained in its previous state. So, we can conclude that when both inputs are 0, then Q and Q complement will continue to remain in their same state. That is, there is no difference between the present and the next state or between the previous and the current state. Or we can say that the value is latched or locked. Check out the second and fourth row of the truth table. The output relies on the previous values of Q and Q complement, which are decided by the values of S and R. Let us see the last combination. What if S and R are 1? As per the truth table of NOR, if any of its input is 1, then their output is going to be 0. Here, the inputs to S and R gates contain a 1. This violates the condition of the latch that the outputs should be the complement of each other, because setting S and R as 1 produces Q and Q complement as 0, which are not the complement of each other. So, this state should be avoided in this circuit which uses NOR gates. The similar situation we came across in NAND gated SR latch when both their inputs were 0. Now, we learned two methods to build SR latch, one using NAND and other using NOR gates. Please note down the differences in the outputs while using these logic gates. So, we are done with SR latches. Let us move on to the second popular latch known as D latch. What is a D latch? What was the necessity of using such a latch? When we discussed about the SR latch, we had a condition where the operation resulted in an unfavorable state. Care should be taken while operating the SR latch so that it never reaches that unfavorable state. We were getting that unfavorable state irrespective of whether we are using the NAND or NOR gate while constructing the SR latch. When we used NAND to construct SR latch, we had such a state when both inputs were 0, and in the case of NOR gates, the state popped up when both the inputs were 1. So, this is a disadvantage of SR latch, and how to eliminate such a state is our next concern. What should we do to get rid of that state? Yes, we should never allow the external input of SR latch to be the same. That is, we should only have the situation where one input is a complement of the other. How can we implement this? The idea is to use one input and negate that value and supply that as an input to the next gate. If we do that, we will never have a situation where the inputs will be the same. When this idea is implemented, the SR latch becomes the D latch. Look at the picture. You can see a D latch constructed using NOR gates. Here the input D is complemented and fed as the input R, and D as such is given as the input S to an SR latch. Now, what happens here? The two inputs of SR latch is actually reduced to one input in D latch. If there is only one input, then you have 2 raised to 1 combinations, that is 2 combinations. So, you tried to eliminate a condition where the latch falls into an unfavorable state, but what happened is one more state where the SR latch retained its previous value is omitted. To explain in detail, the NAND gated SR latch retained the previous state of the circuit when the input S and R were 1. But when we construct a D latch from NAND gated SR latch, this state of the SR latch gets omitted, because you will never come to a situation where both inputs will be 1. Now, take the case of NOR gated SR latch. They retained their previous value when the external inputs to their circuits were 0, but when we construct a D latch from such a circuit, this particular state will be omitted again, and hence the possibility of that circuit to store a previous state value is as such ruled out. Now, you can make out what will be the truth table of the D latch. If you are using a NAND gated SR latch, when D equal to 1, the input S will have the complemented value of D, because it goes through a NOR gate before reaching S and R will have the value of D. That is, when D equal to 1, S equal to 0 and R equal to 1. Now, the working of the D latch is the same as the working of the SR latch when its input was S equal to 0 and R equal to 1. Recall what we had discussed while learning the SR latch. When S equal to 0, the Q will be 1 as per the property of NAND gates, and when Q becomes 1, both the inputs to R gate will be 1, which produces a 0 at Q complement. That is, when D equal to 0, the outputs Q will become 1 and Q complement will be 0. Now, these outputs satisfies the condition of complements, and hence it is in a very valid state. Now, set D as 0, what happens to S and R? When D equal to 0, the input S will have the complemented value of D, because S and R will have the value of D itself. That is, when D equal to 0, S becomes 1 and R becomes 0. Now, what happens to the SR latch when S equal to 1 and R equal to 0? When R equal to 0, the Q complement will be 1 as per the property of NAND gate, and when Q complement becomes 1, the inputs to S gate will have both 1s at its input, which turns the Q to 0. That is, when D equal to 0, the outputs Q will become 0 and Q complement will be 1. Now, these outputs also satisfies the condition of complements and hence this also a valid state. Now, take a moment to pause and check the truth table of the SR latch in the given picture. You can easily understand that if you remove the entries with the same inputs, you get the truth table of the D latch, and hence the D latch can be considered as a miniature of the SR latch. Let us move on to the construction of D latch using NOR gates. So, we use the input D and its complemented value will be fed to the input R and the value of D will be supplied to the input S. Let us set the value of D as 1. What happens to S and R now? S becomes 1 and R becomes 0. What about the SR latch when S equal to 1 and R equal to 0? Since S is 1, according to the working of NOR gate, Q complement attached to the S becomes 0. Now, the inputs to the AND gate are both zeros, which will set the Q as 1. So, when D equal to 1, the inputs S equal to 1 and R equal to 0 and their outputs will be Q equal to 1 and Q complement equal to 0, which satisfies the condition of complements and hence it is in valid state. Now, consider the case when D equal to 0, then S becomes 0 and R becomes 1. What is the output of SR latch in this case? The Q connected to R becomes 0, then both inputs to S becomes 0, which puts a 1 on Q complement. So, when D equal to 0, the input S becomes 0 and R becomes 1 and so their outputs Q will be 0 and Q complement will be 1. This is also a valid state because the outputs are complement of each other. If you check the truth table of the SR latch, then you will get the D's truth table after removing the entries with common inputs. Thus, the D latch overcomes the problem of the SR latch by never producing an invalid or indeterminate state in their outputs. They always have valid values as their outputs, but they can be used only in scenarios where the change in input values triggers a change in the output values. It cannot be used where the circuit needs to hold the previous state when both the inputs change to active low or active high. So, in this video, we came across the SR latch constructed using the NOR gate. Its working is similar to the SR latch made of NAND gates, which we discussed in the last session. The shortcoming of SR latch is that the circuit goes to an indeterminate state when both inputs changes its values to active high or active low. This is rectified using the D latch, which never allows its inputs to be the same. They fixed this issue by using a NOT gate between the inputs so that the inputs will always be complementing each other. So, the D latch is nothing but the miniature version of SR latch when both of its inputs are different. With this, I conclude. Hope you learnt about the SR and D latches and see you in the next session where we talk about flip-flops. Thank you.